Okay, yes, I know what you're looking at. You're looking at 38 minutes thinking, does this say 38 minutes? I have a life. I have things to do. Why would I watch a 38-minute video? Well, let me explain. This video is, in one sentence, the most complicated video in the series. Well, that does include the next episode as well. You're watching this series because you want to learn how to program. I mean, who doesn't? I can imagine the 38 minutes thing there isn't very reassuring. And in fact, when you're halfway through the video, you might be worried that you're going to forget all this or you're not following it. But don't worry about any of that. Here's the entire video. Image 1, Image 2, and Image 3. That is the entire contents of the video. So don't forget to like and subscribe, and I'll see you in the next. No, I'm joking. But that's technically all you need to remember. The only reason this video is as long as it is just because those three images are obviously very abstracted. Don't worry about the fact it's 38 minutes, and don't worry if you struggle a bit in the middle, because theoretically, those are the only three images you need to remember. Okay. Now that you're hopefully a bit cooler with the whole 38 minute and how involved this might seem, let's dive in. Alright, following episode 1, time for some more of our favourite theory. Now, in the last super simple episode, I mentioned a bit about buses and bits and binary, and this video is going to be about the components a computer is made up of. Alright, now, just to test you, let's do quick quiz time with Alex. Is a keyboard an input or output? Okay, yeah, it's an input, come on. But what about a screen? Is that an input or output? This one is an output. What about speakers? Input or output? Output as well, awesome. Before we dive in, let me just make sure we definitely know about the units we use to represent the number of bits. Now, I expect you to generally know these terms, but I just want to make sure that we definitely know these and we know them correctly. We have one bit, right the way at the bottom, right? And 4 of these bits goes into what's called a nibble. I don't really know why it's called that, it just is. 4 bits go into a nibble. We definitely know the next term, a byte. That's 8 bits. Then we go further into kilobytes. And there are 1024 bytes in a kilobyte. Then we have a megabyte, and once again, there are 1024 kilobytes in a megabyte. This is then followed by a gigabyte, terabyte, petabyte, and even an exabyte. So if you didn't know any of those, download the link in the description, at least look at them from time to time, and assuming that you did know what I just explained, let's get into it. Now then, we remember this magical black box that does stuff. Now in the last video, we sort of took the cover off the box, but you see, all of those wires that are inside the computer are split up into groups, and we're going to look at those groups in this video. Okay, as we take the cover off again, I'll just cover the main part of the computer as being in 4 groups. The first group is the CPU. This stands for Central Processing Unit. This is known as the brain of the computer. All of the maths is done in here. All of the code is handled in here. The rest of the computer is managed from here. Without a CPU, the other groups are basically useless because there's nothing using them. Which brings us onto the RAM, standing for Random Access Memory. We also refer to this as the primary storage. This stuff temporarily stores data, which I'll talk a bit more about what that means later. Next is the, what I've titled storage part. This is also known as secondary storage. These things, which once again I'll focus on later, are where all of your files and stuff go. There are lots of different types of secondary storage. Here are some of them. You got the hard drive. You've probably all heard this, but why is it called hard drive? That sounds a bit odd. Well, time for history lesson with Alex here. Back in the day, floppy disks really used to be floppy, and the reason they were floppy was that they were literally made of 2 pieces of paper with a magnetic disc put in between. Now, of course, over time, floppy disks improved in quality, and they started making the casing out of plastic. So they kind of stopped being floppy. But because they used to be floppy, hard drives were obviously a lot more solid, and that's how they got the name hard drive. Now, hard drives are really odd. If you were to look inside a hard drive, the way they work is they have an arm, and this arm goes on top of what's called a platter, and essentially this platter has ones and zeros all around it, and it spins around really quickly. And what happens is that if we wanted to access a file, what would happen is the arm would move on top of the platter and read the ones and zeros off of it. So you know how computers can make this noise? That's the hard drive. That clicking noise is the noise the hard drive makes as the arm moves about. So what's the advantage of the hard drive? Well, it's cheap. Hard drives can go all the way up to 8 terabytes for a pretty low price, and that's because it's really not difficult to make a platter, slap a motor on it, and slap an arm on top of it. But as you might imagine, hard drives are slow. Compared to some of the other secondary storage devices, they are really slow, and that's just because of the whole idea of how they work. Also, they're noisy, which is why they are definitely not good to use in mobile phones. Could you imagine mobile phones being that loud? So that's hard drives. What's next? Well, remember that quick history with Alex just a minute ago? I guess we could also count floppy disks as another secondary storage device, even though no one uses them nowadays. Awesome, well, what's next? What else could we use to store files and stuff? Well, we also have USB sticks, which you can plug into the computer. These still technically count as secondary storage devices, even though they're outside the computer. What else? Well, we have a CD. This goes into a CD drive, and CDs technically still count as secondary storage devices. They can store data permanently, and it can be accessed by the computer. Well, finally, we have the most recent one. SSDs. SSDs are really fast, and they work very similarly to USBs. If you look inside an SSD, it's just a circuit board with a bunch of little chips on it. And these chips can store data permanently without needing any moving parts at all. Most phones have SSDs inside them. Of course, there are disadvantages to SSDs. The first disadvantage is that SSDs are a lot more expensive than hard drives. It costs quite a bit of money to make those chips. And the second disadvantage is that, depending on what you're using them for, SSDs can actually last less time than a hard drive before failing. You see, SSDs have limited write cycles, and these are the number of times the SSD's data can change. Essentially, for some things, it can be better to use hard drives. A perfect example of where SSDs would be awful to use is for CCTV cameras. CCTV cameras are constantly saving all of that video all the time. An SSD would not last that long. We're talking 1 or 2 years, maybe even less, if it was constantly saving hundreds of gigabytes of video. Whereas a hard drive doesn't have this limit. The most common reasons that a hard drive would fail would commonly be things like if the arm hit the platter for some reason, or just the arm stopped working, which is possible because all moving parts fail eventually, or even because the platter literally shattered into pieces because you dropped the hard drive. There are more secondary storage devices, but these are the main ones you would typically expect. Cool, and there's also another section that I've titled I/O. Now, this part stands for input/output, and we already know what that is. These are essentially just sockets that things can plug into from outside. Alright, now, how are these things connected together? Well, all of them are attached to a board called the motherboard. This is the big green board that everything is connected to. Well, it's usually green. It joins up the RAM, the CPU, the secondary storage, and in fact, most of the I/O is actually built into the motherboard itself. Can I just mention, before we hop into real life, yes, we're going to hop into real life in a minute, that there are also some extra components that I'm not really going to get into. You also have the PSU, this is the power supply unit, and it is literally just the part that plugs into the plug socket on your wall. You plug it into the plug socket and it gives the rest of the computer power. There's also the GPU, standing for Graphics Processing Unit, and this is in charge of outputting to the screen and all of that stuff. We're not going to worry about that at all, probably in this entire series, since that's a whole other topic. Right, as I promised, we are now going to dive into real life. Yes, alright, so what I'm going to do now is take a look underneath my desk here, and I've already taken the physical case off my computer so that we can take a look inside ourselves. Now notice that there are fans all around. This is the other reason why computers make noise. Obviously computers produce heat, so we use these to blow air over everything and keep it cool. Now right at the bottom left corner we've got this black box, and this black box is that PSU, the power supply. As you can see, literally all the power supply does is it splits that big amount of power coming in into lots of little amounts of power in each of these little cables. Each of these little cables transfer power to a different part of the computer. Alright, now if we just move back a bit here, you can see that big green board there behind all of the cables is the motherboard. The CPU, the RAM, the GPU and the I/O are all on there. Why don't we start with the secondary storage devices? Now, in this computer, the secondary storage devices are away from the motherboard and they're connected using wires. They're over here behind this metal section. In this computer, right now, I have one hard drive, one SSD, and a CD drive. Right at the top here, we have the CD drive, and you can see it has two cables. The first one is the power cable, and this cable goes right into the power supply. Next we have the data cable, and this data cable plugs into a socket on the motherboard. Look at this here, these are all the sockets that the hard drives and SSD plug into. As you can see, this specific motherboard can only have 6 secondary storage devices, excluding USBs, plugged into it. Next up is the SSD. Look at how tiny this SSD is in comparison to this other hard drive that I have in my hand. Of course, all of the secondary storage devices have to fit somewhere. So what this case has, is it has these little sockets that the secondary storage devices can be screwed into, so that they stay in place. But the SSD was so small, that we had to get this plastic adapter, so that it would actually fit in the slot. Once again, this has power, and then it has a data cable plugging into the motherboard. And finally, is the hard drive, and, well, this is exactly the same, except it didn't need an adapter. It just has a power and a data cable. Awesome, well, those are the secondary storage devices. Now let's identify the CPU, RAM, and the I/O. The I/O is super easy to spot. It's literally attached to the motherboard right here. Right at the back of the motherboard, we can see all of these sockets, which obviously poke out at the back here. Well, now, where's the CPU? Well, it's pretty easy to spot. It's a thing with a massive fan on top of it. You see, the CPU has so many millions of cables inside it that it has this massive fan on top of it. In fact, here's a picture of a CPU. They are tiny, and yet most of the millions of cables that I referred to are inside this tiny little thing. Each cable in the CPU is about 27 nanometers big, and obviously this tiny little thing is going to get seriously hot while it's turned on. So what we have is we have a massive fan put on top of it to help it stay cool. These CPUs are designed to be replaced. You can take the CPU out of this motherboard and put in a newer, more powerful one. Alright, well, let's identify the last component. This is the RAM. Now the thing about the RAM, just like the secondary storage devices, is that you can just add and remove RAM. This is the RAM right here. And notice how it sticks out of the motherboard. Well, the reason is you can take these cards out of the motherboard and replace them with some different RAM cards. So my computer has 8 GB of RAM, right? Each of these 4 little RAM cards here are 2 GB big, so joined together they make 8 GB. Let's say I wanted 10 GB of RAM. I could just take one of these cards out, like I have, and put in a 4 GB card. Then it would all add up to 10. Alright, well, I think that's all the real life stuff we need. Now just in case you're wondering, this big card in the middle is the GPU, and just like the RAM, it's pretty easy to remove. It's only the CPU that's a bit difficult to get out. Also, I know that it might seem like all of these come with the motherboard, but no, they don't. If you go online and buy a motherboard, it won't come with any of these. The only thing that I've described that it would come with is the I/O over here. Everything else, the CPU, the RAM, the GPU, the PSU, the secondary storage devices, the casing, none of it comes with the motherboard. When you build a PC, as I did with this computer here, it's actually really easy to do with a bit of guidance. You choose the motherboard, Then you choose a CPU you want. Then you choose some RAM cards, depending on how much RAM you want. You choose a GPU, a case, this big metal thing here, a PSU, and an SSD or hard drive, or both, whatever you want for secondary storage. And then, after you bought those, all you need to do is just put them together. Put the CPU in the little square socket on the motherboard, put the big fan on top of the CPU, put in the GPU, put the RAM in, connect the PSU to the motherboard, and everything else, things like that. It's really easy to build a PC, it's literally just about connecting everything together. Okay, I've had quite enough of the real world, let's get out of there, and get back to where we were, shall we? Now then, let's decide which one of these components we're going to explain next, and it's going to be the RAM. So, the RAM stores temporary data that the computer needs while it runs. For example, all of the programs you have running, and what state they're in, are stored in the RAM. This is different from those secondary storage devices that you have which store data permanently. The technical terms for this are volatile and non-volatile. Volatile means that the data is lost when it loses power, which is what the RAM is. And the non-volatile, well, means the opposite. It means that the data will stay even when the power is turned off. Very simply, the difference between these two is that the RAM, which is the primary storage, only stores temporary data that's used while the computer runs, whereas the secondary storage stores permanent data, like all your pictures, all the apps you have installed, that sort of thing needs to be permanently stored. But wait a second here. If we have these secondary storage devices that sound so perfect, I mean they can store data permanently and all of that, why don't we just use those for the temporary data as well? Why do we need a primary and a secondary storage? Think about it, why couldn't we just use the hard drive as RAM? Doesn't it seem a bit pointless to have a RAM and a hard drive? Well, actually, there is one major reason why we have RAM, and I can sum it up in one word. Speed. RAM is much faster than secondary storage, and it doesn't matter whether it's an SSD, a hard drive, a USB, it's faster than all of them. Now, there is one issue with this. RAM is also more expensive than secondary storage. For example, video files are massive. Most of the top 100 biggest files on my hard drive are videos. Now, as of uploading this, the typical amount of RAM is 8 GB. That's kind of considered a minimum expected. By comparison, you can have hard drives well up to 8 TB. Now, this all being said, the fact that it costs a lot of money to get a lot of RAM isn't really that big of an issue, because you don't really need that much RAM. Don't forget, RAM doesn't store files, doesn't store videos or anything like that, it just stores some data that a program is using at a time. An example is, let's say if you have a menu open in an app, in the RAM, the app would store whether you have the menu open. Maybe for when you are, for example, browsing the web, it would be data like what page you're on now, how far scrolled down the page you are. That sort of temporary data is remembered using the RAM. So if that's the sort of data that we're storing, it's not really that big of a deal that RAM isn't 8 TB big. The programs that take up the most RAM are programs like video editors, which store just a little ahead of where you are in the video so that it can play quicker. Right then, well, we know the sort of data RAM would be storing. Let's do a very simple example. Opening a Word document. When you double click on that docx file, what's going to happen is your system knows that a docx file needs to open in Word. So what it technically does first is it hops to the hard drive and loads up the exe file for Word, which contains all of the code for Word. All of that code now goes into the RAM. Then your system is going to start running that code, and it's going to tell that code you wanted to open this file. Then the code is going to ask the hard drive for the data in that file, and as the hard drive chucks out the ones and zeros, it will start putting the document in the RAM somewhere as well. Then, once it has received all of those ones and zeros from the file, you'll be able to see it and edit it and so on. Now, you know how you have to click on save all the time, right? Well, you should click on save all the time. Why do you have to do that? And very simply, it's because all of the changes you've made are stored in RAM. The file on the hard drive is exactly as it was before. The only data that's changed when you edit the document is the stuff in RAM. And the simple reason for that again is, that's a lot faster. Trust me, you would know if every single time you typed in a letter, it would save to the hard drive. It would be painful. So what happens is, it doesn't go onto the hard drive until you click on save. And when you do click on save, all it does is just copy the document you have in the RAM on top of whatever was there previously in the hard drive. Of course though, if you don't click on save and you close the program without saving, that data is now gone. It never went onto the hard drive. I mean, if you didn't shut down your computer after closing Word, it might technically still be just sitting there in RAM doing nothing, but it really won't be long at all until some other program comes and uses that space and starts replacing it with its own stuff. So really, it's pretty safe to assume it is gone. So that's how RAM is used. There's one more thing I'd like to mention about RAM, and let's just see first of all if you can work out why this is the case. In 32-bit computers, you can only have 4 GB of RAM. That is the limit. The computer can't handle anything higher. Why do you think that is? Think about how big 4 GB is if you were to put it into a number. I'm sure you remember that 32 bits has a limit, as does 64 bits. But that 32-bit limit is exactly the same as if you were to count every single 1 and 0 in 4 GB. In order to make this just a bit clearer, let's see how computers access the data in RAM. The way that our CPU accesses these 1s and 0s is that it very simply gives each of them a number, and we call this an address, just like an address to a house. This number is where this 0 or 1 is. Address 0 is the very first 1 or 0. Address 1 is the second 1 or 0. Address 2 is the third 1 or 0, and so on. Every 1 and 0 has an address, and it just goes up and up and up. Now, inside a 32-bit computer, this address, well, is 32 bits. So if we had more addresses than 32-bit can handle, which is what we would get if we had more than 4 GB, then there's no way we could give anything that goes beyond the first 4 GB an address. We just can't. So a 32-bit computer can only use 4 GB of RAM. By comparison, a 64-bit computer is all the way up to 4 exabytes. And that's the unit above petabytes. It is massive. Not even Twitter and all of those millions of tweets go into exabytes. Apparently, every single tweet combined only takes up 4 petabytes. Well, I say only, I mean that is still a massive number, but it just shows that the number 64 bits is so big, we definitely won't need to go any higher for a long time into the future. So we've covered RAM very heavily. We've basically gone over I/O as well, so we don't need to worry about that. The most important thing to have taken away from all of that about the RAM is a more logical view on how the computer uses both the RAM and the hard drive together to do things like editing a Word document. Right, now we're at the final thing for this video, and kind of the most complicated part. Yeah, this video really has jumped into the deep end, but bear with me here, okay? This, plus the next video, is literally the most complicated we will learn in this entire series. If you can get your head around all this, I can guarantee you are basically set for the rest of the series. The rest is basically easy stuff compared to this. So, if you can understand this video and the next video, the rest is going to be pretty easy. Now we go on to the CPU. We've gone over everything else. The RAM, the I/O, the PSU, the motherboard, the secondary storage. We've gone over all of it. And all of these are the things that the CPU uses. On their own, everything that I've just covered is useless. Without the CPU, there is literally no point in any of it being there, because nothing would actually do anything with it. By the way, just before we look at this CPU, comment down below if you have a 32-bit computer or a 64-bit computer. To check which one you have, just click on type here to search, and type in this PC. Then right click and click on properties. and it will just tell you right there. So, the CPU, which is also known as the processor, everywhere you hear processor, it refers to CPU, can be split even further into even smaller chunks, as we did with the computer. But right before I do that, there's something you need to know about CPUs, or processors. Everything I'm going to describe on the CPU right here does not apply to all of the CPUs in the world. And that's because different CPUs have different architectures. If you look at, for example, the CPU in a desktop computer and one inside a mobile phone, you'll see that on the inside of the CPU, they're a bit different. Okay, so quick history lesson with Alex here again. There was a guy, okay, called von Neumann. This guy came up with one of the first CPU architectures, which he super creatively called the von Neumann architecture. Now, this architecture was excellent, so excellent in fact, that computers today still use this in some form. But there was a bit of a problem. You know how the code has to be put into the RAM alongside the data? Well, there was something about that really slowed down the computer, and this was so significant that it became known as the von Neumann bottleneck. You see, the CPU could only get one thing at a time from the RAM. So, if we had a bit of code that wanted to get some data from the RAM, it would have to first get that piece of code, and then it would get that data. And this slowed it down a bit. So, instead of only being able to access one piece of data at a time, they would let it access two pieces of data at a time. The idea behind this is that one bus could be used to get the code, and the other could be used to get whatever data the code wanted. So essentially, it could then access two things from RAM at a time. This was apparently so significant that they made a whole new architecture, and they called it the Harvard architecture, which is really strange because it's not even really a new architecture. It's just a beefed up von Neumann that can access two things at once. So to keep it simple, I'll be talking about the CPU as if it's a von Neumann CPU, but just keep in mind that most modern CPUs are a tiny bit different to this in that they can actually access two things at once. Now, von Neumann's overall idea stuck, but as I said at the beginning of this bit, if you looked inside a desktop or laptop computer's CPU, it would be slightly different from a mobile phone CPU. And the reason is that there are two modern architectures which are both based on the von Neumann architecture. Everything I'm going to cover in a minute applies to both of them, since they're very similar, so don't worry about it too much. But it is good to be aware of one of the reasons why you can't just take some code out of the RAM of a desktop computer and then put it into the RAM of a phone or tablet or something like that. Because the code is slightly different, because the architectures are a tiny bit different. Now, don't worry too much about this info, but the first modern architecture is called x86. It's pretty old, it's been around for quite a while. There's also another version of it called x86-64, which is the 64-bit version. So when I say x86, I'm referring to both. This is the one that's found in a desktop or laptop. The other one is the one used in mobile devices, things like your Android tablets, your Android phone, things like that. That one is called ARM. Essentially, anything that needs to be small and portable and doesn't need to be super powerful would have an ARM processor inside it. So, what's so special about ARM processors? Well, ARM processors use up less energy and they produce less heat. The latter is really important because could you imagine having a fan inside a phone? It really wouldn't be very portable. Laptops tend to have fans though because they tend to have x86 processors. Now we've got a very similar question to what we had with the RAM and hard drive. If this ARM is so perfect, then why don't we use it in non-portable devices? And this is exactly the same answer as well. ARM is just slower than x86 processors. x86 is just faster. Alright, enough of all of that architecture rubbish. Just remember this. You have x86 for non-portable devices and ARM for portable devices, and both of these are roughly based on the von Neumann architecture. Right then, let's take the cover off this CPU and see the three main components it's made of. Here it is. The control unit, the register, and the ALU. Right, starting off with the ALU, which stands for Arithmetic Logic Unit. This one is super simple. The ALU is in charge of two things. The first one is arithmetic, which is maths. Anytime you add, subtract, multiply, divide, shift binary, which is something I might mention in a couple of videos later, anything like that, the ALU is used. So now, what about the logic part of the name? Well, it's a bit difficult to fully explain until we've really started coding, but it's the job of this part to do things like comparing two binary numbers. So is this number bigger? Is it smaller? Is it exactly the same? That sort of stuff is also handled through the ALU. Great, that's literally all there is for the ALU. It does math and logic. That's it. Next are the registers. These things are super temporary pieces of data, even more temporary than RAM. Each register is only 32 or 64 bits long, which I know doesn't seem small, but that's only 4 or 8 bytes. And if we consider one letter as 1 byte, that's 4 letters you can store in there. That's barely anything, and there are very few of these registers as well. Summed up, in order for the CPU to do anything, it has to first be put into a register. And that's just because these registers are built right into the CPU. These registers are specifically wired up to the ALU and CU. And because they're specifically wired up to the ALU and the CU, they're even faster than RAM, which is kind of also why they exist. Right, well, we've come around to the final part of the CPU, the control unit. Now, the control unit is essentially in charge of managing, well, really everything. It's the part that's in charge of communicating with the RAM. It's the part that's in charge of executing instructions. If the CPU didn't have a control unit, it would be very much like a computer without a CPU. There would be no point in there being an ALU and registers because there's nothing actually using them. Okay then, that's each of the components covered. Let's see how these all work together. Let's say we had the number 3 in RAM and we wanted to add 4 to it. Well, this number has to go into a register first. So, the number 3 gets copied into, let's just call it register A, and this now contains 3. So now all we need to do is add it. So what the CU does is it essentially talks to the ALU and asks it to add 4 to register A. So then the ALU goes in, does its magic, and we now have 7 in register A. And then to finish it off, the CU will then go in and copy that 7 back into the RAM. And there you go, we just added 3 and 4. This happens thousands and thousands of times per second. So just remember, as you use a computer, be it a mobile phone, a laptop, a desktop, whatever it is, just remember that it's doing thousands and thousands of register swaps inside the CPU every second. And now it's time for us to quickly revise over all of that. Obviously, I am not going to be able to fit all of that onto one screen, so I'll put it into a bunch of different categories. And once again, if you really feel like it, you could actually go ahead and make them your background. Right, let's start off with the components. If we look deeper into the computer, we'll see it's split into 4 parts. The CPU, the RAM, the I/O, and the storage. The CPU is considered the brain of the computer. It controls all the rest of it. It controls the RAM, it controls the I/O, it controls the storage, it controls everything. Without the CPU, there wouldn't really be a point in there being anything else. The RAM, also known as primary storage, stores temporary data like what apps are running and what state they're in. The RAM is volatile, which means that when the computer turns off, all of the data in the RAM is lost. So then, if that's the case, then what happens to all of the files? Well, they go into the storage devices. The storage devices store data permanently unless they fail. Things like your pictures, files, and apps are put onto the storage devices. And finally is the I/O, which is super easy to remember since that was literally the topic of the last video, inputs and outputs. These are usually directly on the motherboard, which reminds me that all of these components in some way are attached to the motherboard. Some of these are directly on the motherboard and some are connected using cables. Cool, there it is, download link in the description. The next topic is what secondary storage devices we have. Well, we have a hard drive. This is called a hard drive because floppy disks used to be floppy and by comparison, hard drives are just more solid. These things have a moving arm inside them which goes on top of the spinning platters. We also have CDs and USBs, which I'm sure you already know about. And then we have the SSD. This is the latest addition to the list, and the SSDs are a lot faster than the hard drives, and they don't have any moving parts inside them. However, they have limited write cycles, which means their data can only change a certain amount of times. This means that SSDs are best for places where the data doesn't change a lot, like, for example, an archive. It would be fast. SSDs would definitely last a lot longer than a hard drive if all you do with them is just load from them. But for something like CCTV cameras, where the data is constantly changing, thousands of gigabytes every second, they're really not a good idea because they're not going to last very long. Which brings us on to the final topic, the CPU. When we look inside the CPU, we'll see three things: the registers, the ALU, and the CU. The ALU is the easiest one to remember. This is the arithmetic logic unit, and this is where all of the maths and logical things happen. Next we have the registers. These are really tiny little storage areas for the CPU, each of them only being about 32 bits or 64 bits. These things are even faster than the RAM, because they are wired directly with the ALU and CU, whereas the RAM has gone through the motherboard, which slows it down a bit. Finally, we have the CU. This is the control unit. This is essentially controlling the entire process of running code, moving data in and out of the registers, and things like that. Okay, so there's the CPU. Go ahead and download these if you want. And that is this video, summed up in 3 screens. These screens, by the way, are great for revision. So, I suppose the final question is, what is the next video going to be about? Well, the next video is going to be about software. You know how I kept on saying that code in the RAM? We've been looking at the hardware so far, which is the physical stuff. So now, we'll start thinking about how the computer knows what code to run when it boots up, or how your programs are managed, things like that. And that's what there is for this video. But don't forget to post that comment saying whether your computer is 32-bit or 64-bit. If the next video is out, it's going to say right over there. So take a look at that. Maybe also click on the subscribe button, and I will hopefully see you in episode 3.